Okay, Chapter 18, Problem 55. In this problem, we are told that there's a 0.65 millimeter diameter copper wire carrying a tiny DC current of 2.7 microamps. We're supposed to estimate the electron drift velocity. And so if you recall, the way to think about this is you've got a wire, and in this wire there's some current, which I'll call I, and in this particular problem, 2.7 microamps, or 2.7 times 10 to the minus 6 amps. The picture here is that electrons are the charge carriers, so there's a whole bunch of these little things, like this. Each one of them has a charge. The charge of the electron is equal to minus E, right, where E is 1.6 times 10 to the minus 19 coulombs. So a tiny amount of charge per electron, but then again there should be a lot of electrons. The relationship between the current, I, and the electron charge, let's see, if we were just interested in the magnitude of this, not worrying about the direction, it's related to the charge of the electron, the charge carriers. It also depends on the number density of those electrons. Okay, so if you like, this is coulombs times something with 1 over meters cubed. It also depends on the area of the wire, that is to say the cross-sectional area A. And then lastly, it's going to depend on how quickly the electrons move on average. That's called the electron drift velocity. I'll call that VD. Okay, and the units should all work out. Here we've got units of meters squared. This has meters per second. I'm going to write that down actually. This is, if you like, this is coulombs. This is meters to the minus 3. This is meters squared. And this is meters per second. So meters to the minus 3, meters squared, meters, all the factors of meters cancel, and you're left with coulombs divided by seconds, coulombs per second, or amps. So this formula works out. In this problem, we're supposed to figure out what the electron drift velocity is. So let's use this to solve for VD. A little bit of algebra shows you that I divided by the charge of the electron, the number density of the electrons, and the cross-sectional area of the wire. That's the formula we're going to use to solve this. They tell us what the current is. We have the charge of the electron. Getting the area of the wire is not so bad. The area of the wire should be, well, it's the cross-sectional area of it. It's, in other words, the area of a circle, pi times radius of wire squared. And they tell us the diameter of the wire, at least, it's 0.65 millimeters. So we know that the radius of the wire is, I'll just write this down, 0.65 millimeters divided by 2. So perhaps what we should note is that the most complicated thing in this whole problem is going to be estimating the number density of the electrons. I'm going to go ahead and write some stuff down. We have our current. I'm going to go ahead and underline that. The area, when we plug everything in, I'm going to write this number down, 3.32 times 10 to the minus 7 meters squared is what I get when I stick this number in, convert to meters. So we have our area, and we have our charge. So the last thing to do is estimate what is the number density of electrons. Okay, so what is this? Now we're told that this is a copper wire. And the estimate that we're going to make, or the approximation we're going to make, is basically one free drifting electron per atom. So what that means is if you identify one electron for every one atom, that means the number density of electrons that we want in this formula is equal to the number density of copper atoms. And that is not so hard to calculate when you think about relating the number of copper atoms per unit volume to the mass of copper per unit volume. Okay, so that relationship there, so let me remind you of something that we have hopefully talked about in class. The mass density of copper should be seen as, well, it's the total amount of mass of copper in any given volume divided by that volume. Okay, but this can also be thought of as the number of copper atoms times the individual mass of a particular copper atom and divided by that volume. And it's the number of copper atoms per unit volume. That is what we're talking about here. That is the number density of copper atoms, and that gets multiplied by the mass of a copper atom. So what we need to do is, given information we know about copper, in your textbook or online, you can look up that the mass density of copper is known. That's approximately 8.9 times 10 to the 3 in units of standard SI units, kilograms per meter cubed. The mass of a copper atom, well, that you have to remember that that's something that can be figured out because the at least the mass of copper is can be written as its atomic mass can be written as 63.5 approximately grams per mole, or if you like, that's 0.0635 kilograms per mole. And as long as you can keep track of what a mole is, let's write this. Let's go ahead and write 0.0635 kilograms over moles, and recall that 1 mole is the same as approximately 6, maybe 6.02 times 10 to the 23. So in doing that, we can therefore figure out how many copper atoms we have to deal with. So let's put all this together now. We're trying to solve for the number density of copper. Apparently the number density of copper is equal to the mass density of copper divided by the mass of an individual copper atom. Okay? This is 8.9 times 10 to the 3 kilograms per meter cubed. Divide this by the mass of copper. In other words, 0.0635 kilograms per mole times 1 mole divided by 6.02 times 10 to the 23. When all is said and done, what you should find here is that this is approximately 8.44 times 10 to the 28 per meter cubed. In other words, I'll write this as 1 over meter cubed, or if you like, meters to the minus 3. Okay? With all that done, we are now ready to plug that into our formula for the electron drift velocity. So let's carve out a little space and do that here. Vd is the current, 2.7 times 10 to the minus 6 amps. The charge, 1.6 times 10 to the minus 19 coulombs. This large number, 8.44 times 10 to the 28 per meter cubed. And finally, the cross-sectional area, the 3.32 times 10 to the minus 7. 3.32 times 10 to the minus 7 meters squared. If all the units are correct and I haven't screwed things up too much, this is actually a fairly tiny number. It's about 6.0 to be more precise, times 10 to the minus 10 meters per second will be your electron drift velocity.